So last time we finished talking about the mathematical stuff that we need. And now we're going on to the first kind of dynamics topic. So our new topic, our first topic, is particle kinematics in non-rotating coordinate systems. And later on, one of the last topics that we're going to do is going to deal with rotating coordinate systems.
Kinematics, that's pertaining to accelerations and velocities. That's just like the formal name for that.
Kinematics you can think of that as describing motion without dealing with the causes. And the causes would be like force, mass, and energy. So kinematics is all stuff you could do from a videotape of something. You know, if you had measurements all out in your room and you could time things from the video and see how far they went, you could do these calculations. From a video, you can't tell how much mass something has or how much force is being applied. So we're not dealing with those. But this is relationships between time, position, velocity, and acceleration. And you can have kinematics of rigid bodies. You can have kinematics of deformable bodies. This is kinematics of particles. And the meaning of particles is you tend to think, most people tend to think of particles as small. That's not necessarily the case. A particle is just something that so it's a mathematical treatment of an object. As existing at the center of mass and having no length dimensions. So it's the size of a point, you know, it has no size at all, and it's just moving around, and it represents the center of mass of the object. And this is kinematics, so we're not dealing with mass yet, but a particle does have mass. It just doesn't have size. Using Newton's laws, which is what we're going to do here, you can treat anything as a particle. If you don't care about the object's orientation. You can't do that using an energy approach. So you have to be careful when using an energy approach. But we're not going to do that yet. But the reason is that when you're using an energy approach, you know, basically you think of potential energy and kinetic energy going back and forth. Well, bodies have translational kinetic energy, but they also have rotational kinetic energy. And potential energy can be exchanged with rotational kinetic energy too. So, and a particle doesn't have rotational kinetic energy. So if you try to so like, for example, if you have something rolling down a hill and you plan on treating that thing as a particle, it starts with potential energy. A lot of that potential energy goes to making it rotate. And so you'd be wrong about the speed that you have at a certain point. But using Newton's laws, you can treat anything as a particle if you don't care about orientation and moments and stuff. Okay, and then non-rotating coordinate systems. So that's important. You've never dealt with rotating coordinate systems before, but we will later in this class. And we're going to do sort of 4 sections in this topic, under this heading. The first one is the time derivative relationships. So acceleration, the acceleration vector is the time derivative of the velocity vector. That other one's open, I think, right? They'll make it. Yeah, if they're smart. Okay, so we have those time derivative relationships. And we've already talked about how to take time derivatives of vectors in non-rotating coordinate systems, so we know how to deal with that. The second section is the chain rule. And we're going to use the chain rule when we can express the velocity vector as a function of the position. This comes up probably most naturally if you're using an energy approach to come up with speed as a function of position, okay, then you can often come up with the velocity vector as a function of position. Well, you don't have it explicitly as a function of time, but you can use the chain rule to get through it, and we'll talk about that. And then the third thing is circular and spherical motion. So that's something moving a constant distance from some center, okay? A constant radius around some center. And in 2D, that would be a circular motion. In 3D, that would be a spherical motion. And then the last one is relative motion. We'll see that this works really naturally with circular and spherical motion. And these two together are very useful for linkages, which is collections of rigid bodies connected by joints. Okay, so the first one is the derivative relationships that says the acceleration is the time derivative of the velocity, is the time derivative of the position, or acceleration is the second time derivative of position. So the one main thing that you have to understand about this is that you don't want to think for example, velocity is the derivative of the position. It has to be a time derivative. And so if you have the well, and same thing with acceleration. Don't think of acceleration as the derivative of velocity. So like, for example, if you have the velocity given as a function of x, you can't just take the derivative with respect to x and think that that's the acceleration. You can only take the derivative with respect to time to get the acceleration. Okay, there's two directions you can go with these derivative relationships. The first one is you can go in the direction from position to velocity, or velocity to acceleration. In that case, having a function of time is enough. All you have to do is take the time derivative. So, for each step, you're just taking the time derivative. So like, for example, if the position vector is t squared, then that means that the velocity vector is just the time derivatives of those components. So it's 1, 2t. And that's velocity as a function of time. And that's clear that that position is a function of time, that velocity is a function of time. If you want to know the velocity at a specific instant, just plug in the time that you care about, and it'll give you the vector. And then the acceleration as a function of time is 0 for x, 2 for y. Also go the other direction. So where you're going from acceleration to velocity or velocity to position. In that case, having functions of time is not enough. Because in this direction, you're solving a differential equation using separation of variables. So each step, going A to V or V to P, is a separation of variables problem. And that means you need one boundary condition for each component. So for example, let's say that you know that velocity as a function of time is equal to t squared cosine t. What's the position as a function of time? Well, just intuitively, this is telling you how fast something's moving and in what direction, okay? But it could be happening right along the ground, or it could be happening 30,000 feet up in the air. Obviously, that information is important to come up with a position function. So that's what you need for the boundary conditions, okay? And so since we're thinking of things at least in 2 dimensions, it could be way up in the air, or it could be down close to the ground, or it could be here, or it could be, somewhere in Russia or whatever, So you need the boundary condition information to say where that position is starting. So the boundary conditions would be given something like this. So say that we're given that the position vector at time equals 0 is equal to 0, 50.
When you say one boundary condition for each component, you mean the x and the y?
Yeah, that's right. Okay, so at that point, you can say, so you can think of that velocity vector as an x and a y component. And we know that dx dt, that's the x component of the velocity, is equal to t squared. And so dx is equal to t squared dt. And now we can integrate both sides. And we get that x is equal to t cubed over 3 plus c. And now we'll use the boundary condition. The boundary condition says when time is equal to 0, x is equal to 0. So x is equal to 0 when time is equal to 0. And that lets us calculate that c is equal to 0. And so from that, we know that the x position as a function of time is just t cubed over 3. And now we go to y. This is, so when you're doing this with vectors, what you're doing is an uncoupled system of ordinary differential equations. Okay. The x stuff stays in the x equation and the y stuff stays in the y equation. So you can just do them as separate, 2 separate differential equations, or 3 separate ones if it's in 3D. Okay, so now the y equation says dy dt is equal to cosine of t. So dy dt, which is just another way of writing the y component of the velocity, is equal to cosine of t. So dy is equal to cosine of t dt. And you can integrate both of those. And you get that y is equal to sine of t plus some other c, I'll call it c2. And now use the boundary condition to find c2. The boundary condition for y says when time is equal to 0, y is equal to 50. So plug that into this equation and we get 50 is equal to sine of 0 plus c2. Sine of 0 is 0. So c2 is 50. And so y is a function of time is sine of t plus 50. And so then put these two together, you know, the position vector as a function of time is x component, t cubed over 3, y component, sine of t plus 50. And so now plug in any value at time and it'll give you the position vector, which the position vector you can also just think of as the coordinates of the object at that instant.